Alright guys, so now we're going to look at log and exponent graphs, now that we know a little bit about logs and exponents. So the first thing that we're going to do is look at the parent function. So my exponential parent function can have different bases, but it's basically your base raised to the variable as your exponent. So to see what this graph's going to look like, we're going to start with a t-chart, and I'm going to pick some easy basic points to see what it's going to look like. So for example, if x is 0, 2 to the 0 power is 1. If x is 1, 2 to the first power is 2. If it's a negative 1, though, that makes it a 1/2. And then to see what this graph does farther, let's pick a point pretty far along. Like if I picked 5, 2 to the 5th would be all the way up at 32. And then the negative 5th, that would be 1/32. So that can help us see what this graph's going to look like. I'm going to go through the point 0, 1, 1, 2. And then this graph is going to get really, really small, and then it's going to get really, really big. Now, because your base can be different, we're going to look at the points that are going to be consistent no matter what that base is for your parent function. And the first one is 0, 1. No matter what your base is, the parent function is always going to go through the point 0, 1, because any number raised to 0 power is 1. The other point you're always going to have is 1, comma, the base, because any number raised to the first power is still itself. And then finally, if you look here, there's a little horizontal asymptote, because there are no negative values at y equals 0. Now this is going to be what your parent function will look like every time for every base, as long as that base is greater than 1. Okay, if you look down here, there's an example of your base being between 0 and 1. So if that base is smaller than 1, its graph is going to look a little bit different. For example, here I have y equals 1/2 x. If you think about that, if I have 1/2 and I raise that to, say, the 5th power, that number is actually going to get smaller, because 1/2 to the 5th power is 1/32. So this graph will still go through 0, 1, and it'll still go through 1 comma my base, but the way that shape is going to go is going to be in the opposite direction, because as my x's get bigger, that y value is actually going to be getting smaller. So now that we know a little bit about what the parent function looks like, we're going to review some transformations. Now we've talked about these already this year, and you learned about them in Algebra 2. But transformations, remember, there are vertical and horizontal transformations. So this first one is a vertical transformation. That is a vertical shift, and it's going up 1. Because that plus 1 is outside of the parentheses. So if it's away from the x and outside of it, then it's a vertical shift. So what I would do here is take my y-coordinate and add 1. Now that minus 1, that's going to be a vertical shift, but this time it will be down 1, which means I would take my y-coordinate and I would subtract 1. Now the next one, the plus 1 is actually with the x, so that means that's going to be a horizontal shift. Remember that horizontal stuff is backwards from what you think, so it's going to shift to the left 1, which means I would take my x-coordinate, in this case, and I would subtract 1. X minus 1, remember that minus is with it, so it's a horizontal. The horizontal stuff's backwards, so that's a shift to the right 1. And that means that I would take my x-coordinate and I would add 1. Then the next two, those are both reflections. Now they get a little bit confused as to which one's which. Now this first one, the negative is with the x, which means it's a horizontal change. So that means my graph is going to reflect horizontally, which is across the y-axis. Okay, so it's going to reflect across the y-axis. What I'll actually change, though, in this graph is the x-coordinate. I'm going to have a negative x-coordinate because it's changing side to side. Okay, similarly on the next one, I'm going to have, this graph is going to reflect over the x-axis, which is going to give me a negative y-coordinate. Now the easiest way to draw these exponential graphs with your transformations is to come up with your parent function points, and then just see what transformations we're making to them. So for example, on this very first one here, my original parent function always goes through 0, 1, 1 comma the base, and the base is 5, and it has a horizontal asymptote at y equals 0. So now all we need to do is see what kind of changes we're making. Well, if you look at this one, I have a horizontal shift to the right 2, so my x's are going to add 2. Then I have a vertical shift up 4, so my y's, I'm going to add 4. So I just apply those transformations to each of my points. So that means my new points are going to be at 2, 5, 3, 9, and my y equals line is only going to shift up. You can't really tell if it shifts side to side because it's still a full line. so at y equals 4. And once I have my new points, it's pretty easy to draw my graph. So I'm going to go through 2, 5, and 3, 9, and I have that horizontal asymptote right below it. Alright, same idea on the next one. I'm going to come up with my parent function points first. So the first point on there is going to be 0, 1. 1 comma the base, my base is 3. And then I have the horizontal asymptote, y equals 0. So then my new points, I need to look at the transformation. The only transformation I have on this one is that negative out in front. It's out in the front, not with the x, which means it's going to reflect vertically, so it means that I'm going to have a negative y coordinate. So I'm just going to take all of my y coordinates from my parent function and make them negative. And then I can graph my new graph. And there's my exponential functions. All right, next we're going to look at log functions, and these are going to be a little bit different, so we need to be careful. Okay, now if you look, the log parent function is the inverse of the exponential function. And what we learned about inverses means that we switch our x and our y's, and it also means that the graphs are mirror images of each other across the line y equals x. So again, to see what this graph is going to look like, I'm going to start with an example, which is that y equals log base 2 of x. So I'm going to pick some easy x values to get me some good points. So the first one I'm going to pick is 1. So if you think about it, remember, a log is a rewritten exponent, so 2 to the y power is equal to x. So that means 2 to the 0 power is equal to 1. If I pick an x value of 2, 2 to the something power equals 2, that has to be 1. And then if I were to pick a number like 16, 2 to the 4th power gives me 16. So if you look at this graph, I'm not going to have any negative exponents. We already talked about this a little bit. You can't have a negative argument. So what that means is this graph is actually going to have a different kind of asymptote. And that's the easiest way to tell the difference between your exponential functions and your log functions. Because this graph has a vertical asymptote instead of a horizontal asymptote. So just like our exponential function, there's 3 things in this graph to take note of. First, I have a vertical asymptote at x equals 0. I go through the point 1, 0. And then I'm also going to go through the base, comma 1. And if you remember, those are the exact same points as my exponential function, but my x and my y are flipped. And if I were to graph that exponential function, it would look a little something like that, which is a mirror image over that line, y equals x. Now, transformations on your log graph, again, pretty much the same thing. If your plus 1 is with the x, that's a horizontal change, and that horizontal change is backwards. So in that case, I would take my x coordinate and subtract 1. The one below that, that plus 1 is outside the parentheses, away from the x, so that's a vertical change, and it's going to go up 1. And again, my negatives, I got to make sure I have them right. In the parentheses is a horizontal change, so that means I make my x's negative. Outside the parentheses, that's with my y's, so I make my y's negative. So now we're actually going to graph 2 log equations, and those are the 2 that we actually just talked about. So what I'm going to start off with here are the parent functions for that base. So if I have a base of 2, my parent function points are going to be 1, 0, my base, comma 1, and the asymptote x equals 0. So on the left, I'm going to graph that one, pick those new points in yellow. So the negative on the outside means I make my y coordinates negative. So I take my parent function points and make those points negative. So that graph is going to go through 1, 0 and 2, negative 1, and it still has that asymptote. So it's going to look something like that. Whereas the next one, let's do that one in blue. The negative is on the inside, so that's going to affect my x-coordinates. So I take my original parent function, but I make my x-coordinates negative instead. So this graph is going to be reflected the other way. And I still have that asymptote over here. Now one thing to look at here are my domains. Okay, so the domain of my parent function and the domain of the negative log of x were both the same. Those domains were from 0 to infinity. But this graph over here, my domain is from negative infinity to 0. The way that we find our domain is based on the argument. So if you look at what's in parentheses, we base our domain on where that cannot equal 0, where that has to be greater than 0. So I take whatever is in the argument and I make it greater than 0. So in this last example down here, that's the strategy I'm going to follow. I want to find the domain of this function. So all I know is that that argument in there cannot be a negative number. So I just take that inside and set it greater than 0 and solve the inequality. So I can subtract 6, divide by negative 3, or divide by negative 2, and be careful. When you divide by a negative number, you have to change the direction of that inequality. So that means my domain is everywhere that x is less than 3, and if I want to write that in interval notation, that would be from negative infinity to 3.